Hey everybody, Mr. Judson here. So we spent the last couple videos talking about law of sines and law of cosines, and so really we need to work some story problems into this. And so I think the way that I'll do this is I'll just lay my book down here and kind of zoom in on a problem. I'll have you guys try it, rather than me trying to write the whole problem down. And then I'll come back and work it. Okay, kind of like in class how I would copy a problem from my computer onto the smart board and then we'd work at it from there. Okay, so first one we want to take a look at. This is on page 444, so if you wanted to grab your book and use that, you could certainly do it. We're going to go ahead and take a look at number 34, so let me zoom in on that. Alright, so the directions here say to determine the angle theta in the design of the street light shown in the figure. Alright, so we're trying to find this angle right here. This side is length 2, this side is length 3, and this side right here is length 4.5. Okay, so you guys go ahead and try that. Remember, Central Washington doesn't like to give pictures. Our book likes pictures, but a problem like this, they would have to give us a picture to work with. Okay, let's see if we can find that angle. All right, so I'm not sure that this is really a story problem. This is more like here's a picture, find the missing angle. But we would look at that and say, okay, if I'm looking for that angle, I'll leave it as theta. I know that if I take any side and square it, that equals the other two sides squared and added together. I'll just go ahead and square those in my head. Minus twice the product of those two sides times the cosine of the angle that's opposite 4.5, which is theta. That's the piece we're looking for. Alright, so let's see, I'll use my calculator here to square this. And I get 20.25 equals 13 minus 4 times 3, that's 12 cosine theta. I now need to move 13 over here and subtract it. So when I do that, I get 7.25 equals a negative 12 cosine of theta. And so now I'll move that negative 12 over and divide. So 7.25 over a negative 12 equals cosine theta. And now I'll do the inverse cosine of this. So on the calculator, I'm just thinking second cosine of 7.25 divided by negative 12. So I got theta equals 127.169 degrees. There's my answer. I did what they asked for. Alright, let's try another one. Alright, so the next one we're going to do here is number 35. It says that two ships leave a port at 9 a.m. So I told you guys this was coming. Hopefully law of sines and cosines will make this a little bit easier for us. Two ships leave a port at 9 a.m. One travels at a bearing of north 53 degrees west. So remember, that means you point north and rotate towards the west. So we must be on the west coast. At 12 miles per hour. I don't know why they didn't say 12 knots per hour, but oh well. The other travels at a bearing of south 67 degrees west at 16 miles per hour. Approximate how far apart they are at noon that day. So they left at 9 a.m. They must have traveled for 3 hours. Okay, you guys go ahead and try that. Alright, so here's point P for port. And I drew a compass in here. So it says the first ship starts at with a bearing of north 53 degrees west. So you start north, rotate towards the west. So this angle right here is 53 degrees. All right? And the other ship South 67 degrees to the west. This is south down here, this is west. This would be east. And so, let's see, the first ship was doing 12 miles per hour. It went from 9 a.m. to 12 noon, so that's 3 hours, which means 3 times 12, this would be 36 miles. And the other ship was traveling at 16 miles per hour for 3 hours. So that would make this 48 miles. All right, geez, look at that ink bleed together. And so the question we're trying to answer is, how far apart are they at noon? So I'll just call this x. That's what I'm trying to solve for. So if you think back to how we did this previously, oh my gosh. We had to extend this out. We had to get a triangle here, a right triangle, and then the bigger right triangle. And then I'd probably have to do the same thing up here, draw a line down, and I'd have 4 different right triangles that I'd be trying to work with. And now all of a sudden, I've got law of sines and cosines, and we've really made this a pretty easy problem. Back in chapter 4, you guys didn't get one this hard. This would have been rough. Okay? Geez, that's hard to read. Let me fix this. $48. All right, so the first thing I need to do is I need to figure out what this angle is in here. And so if I add these 2 angles together, I would get 120 degrees. Subtract that from 180, that means there's 60 degrees left inside there. And at this point, this looks like the last problem we did. Any side squared is equal to the other 2 sides squared and added together minus twice the product of those 2 sides times the cosine of 60 degrees. And so this is one where my variable is already by itself. I just need to put all this stuff into the calculator. So 48 squared plus 36 squared minus 2 times 48 times 36 times the cosine of 60. And I'm still in degree mode. So I got x squared equals 1872. And so if I take the square root of that, I get x equals 43.267 miles. Now, remember, normally when we solve and we take the square root, we include the plus or minus sign. A negative distance doesn't really make sense in this problem. And so that's why we're just answering with a positive measurement. Wow, that was so much easier than back in chapter 4. Right? If we didn't have law of sines and cosines, this would not be a very easy problem for us. All right, let's try another one. All right, so let's try this one. See, an airplane takes off with a bearing of 72 degrees. So remember, airplanes always start at north and then rotate counterclockwise however many degrees that is. Okay, ships do the north so many degrees, east or west or whatever. And it's flying at 300 miles per hour. After 2 hours, the plane changes course to a bearing of 115 degrees and flies for 1 more hour. How far and at what bearing is the plane from the airport? So let's just start with a picture. You guys go ahead and draw a picture of what this looks like. Before we do any work, make sure we have a good picture, and then we'll go from there. Alright, so what I'm going to do is I'm going to draw a compass here. This is north. This is my east-west line. And this is our airport. Plane starts right here and it flies at a bearing of 72 degrees. So I start north, I rotate 72 somewhere down in here, and the plane flies this direction at 300 miles per hour for 2 hours. So that would be 600 miles. And this angle right here is 72 degrees. It then changes course. So let me draw another compass. Here's north to 115 degrees. So there's 90. I gotta go a little bit past that. And so the plane is now going to go this direction for 1 more hour. So 300 miles. So if this was 115 degrees from here, 115 minus 90, that would make this 25 degrees right there. All right? And so our question now, and I really don't know, is this line above or below this east line if I extend it out? I really don't know. But what I'm trying to answer is, what is this distance? We'll call it x, and at what bearing? So I'm gonna have to find this angle right here. All right, so I guess to start, I have 2 sides of my triangle. If I could get this angle, that would certainly help. And so, yeah, let me let you guys think about that for a minute. Go ahead and pause the video and see if you can finish this up. So again, if we're back in chapter 4 and you think, where do I draw the right triangles? Oh my gosh. I was trying to think about that and my head's kind of spinning just trying to figure out where those go, and yeah, I don't know. That would be a really hard problem. But finding this angle right here isn't really that difficult if we remember that when you extend an east-west line and it eventually intersects with a north-south line, that right there is a right angle. And so I do have a right triangle here, where if this is 72 degrees, I ought to be able to figure out what this angle is. Right? That's 90. I got 90 left, so 90 minus 72, that's 18 degrees. And so I'm going to put 18 degrees right there. So now if I add those 2 angles together and subtract from 180, I should be able to get this one. So this angle right here is going to be, let's see, what is that, 35, 43, 180 minus 43, that'd be 137. And now I've got a side angle side, and so I should be able to figure this out right here. Okay? X squared equals 300 squared plus 600 squared minus 2 times 300 times 600. God, sorry, my pen's falling apart here. Cosine of 137. So just to remember this, obtuse angles are only a problem when you're looking for them, when that's what you're trying to figure out, and it's only with law of sines. If I already know the obtuse angle, there's not going to be any problems at all. Whether you're using law of sines or cosines doesn't matter. All right? All right, so I'm going to punch all this stuff into the calculator. I've got 300 squared plus 600 squared minus, I'll do 2 times 300, that's 600, times 600, okay, 600 squared, cosine of 137. And so what I got is x squared equals 713 287.333. And so now I just need to take the square root of that. So square root of the last answer, and I got 844.563. That's how far the airplane is from the airport. Okay. Now, why would an airplane do this? You know, maybe there's some bad weather and it's trying to go around it. I think that kind of thing happens all the time. That way you don't get as bumpy of a ride. There's not as much turbulence. But now I need to figure out the bearing. And so if I could figure out this angle right here, let me just call this angle alpha. If I could figure out that angle, all I have to do is 72 degrees plus that angle, and then I have theta. And we could use law of sines to do that because we now know an angle and its opposite side. This side x is 844.563 miles. So if I set up a law of sines here, let's see, I'm trying to find alpha, so I'm going to say sine of alpha over the opposite side, which is 300, equals the sine of 137 over 844.563. And to get sine of alpha by itself, here I'm dividing by 300, so I'm just going to move that to the other side and multiply by 300. And so what I get here is sine of alpha equals, so I'll go to my calculator, I'm going to do 300 sine 137, close parenthesis, and then divide that by, I'll arrow up and get the last answer, so I keep things exact. And so I got 0.242. And then I'll do inverse sine of that. So second sine of last answer. All right, I just saw that this was a little bit off the screen. So second sine of this number, and what I get is 14.020 degrees. So alpha equals 14.020 degrees. And so now what I want to do is I want to take that angle and just add it to the 72. Right? 72 is from north down to this line. So now add that, you would get 86.020. So it's this far from the airport at 86.020 degrees. There's my answer. And I'm kind of short on space here. What I should do is, make sure I make this clear at the end. The plane is 844.563 miles from the airport at a bearing of 86.020 degrees. Okay, always want to make that answer nice and clear. So this is a problem that, again, in chapter 4, this would have been like one entire homework assignment because we'd have to draw so many different right triangles to figure this out. It would just be a lot of work. Now all of a sudden we're in chapter 6. We know law of sines, law of cosines. It's a little bit easier. All right, that's what we have for today. Let me get you guys an assignment. All right, here we go. We've got number C19. It's on page 443, 444. We're going to do 36, 37, 40, and 41. All right, that's it, you guys. Have a good weekend. I'll see you on Tuesday. We've got really one more thing to talk about, and that's the idea of vectors. Vectors are something that I think is helpful for anybody who's planning on taking physics. It's a way that describes motion and forces acting on things. And so our airplane problem we'll take that and we'll add something different to it next week. We'll have wind pushing on the plane and the question, how far does it blow the plane off course, things like that. All right, so have a good weekend. You guys stay safe. See you next week.